we should be clapping for you guys for being such troopers and staying here to the end. So I'm Maya, and Roger and I are going to tag team here. So our title is, we really want to use persistent memory, but we are hitting bumps in the road. And so what we want to tell you is some of our use cases and what we have learned from them, and what some of the experiments and software we've developed. And we have open source software, as well as some stories for you of how we've used it and what we've learned. So being a national lab, a DOE lab, we have a lot of data. So we have data from our simulations, we have data from experiments, we have data from different sorts of sensors. And for the past, I guess it's been 10 years at least, we've been looking at application drivers, and in particular, for this talk, I'm going to talk about metagenomics. What's that? I'll tell you. Astronomy and graph analytics, and what we've learned in trying to use flash SSDs, so what was available at that time, and going through this past decade, what we learned from it, and what our ongoing projects are all about. The people who are involved, I'm showing here, we have a library, a user space library called UMap, and we have a number of people working on that. We have recently done some studies with Optane, certainly not to the depth that we've already seen. Kai and Dong Li from Merced are helping us to evaluate UMap, and Xiao and Jishen also participated in that project. Roger is our graph guru, and I have been PI of the various persistent memory projects, including processing near memory. So I'm interested in a very broad range of topics related to memory. At the national labs, and in general with HPC, there are an increasing number of HPC systems containing flash. So the traditional use is, Gary Greider came up with this name, burst buffer, which I think is a really unfortunate name, but it's a way to have intermediate storage to checkpoint. So for a distributed memory computation, having all the nodes doing a checkpoint. And so SCR is a library that was developed at Lawrence Livermore Scalable Checkpoint Restart. And I think we got Catalyst, 10 years ago, maybe. So Catalyst was one of our first 300 node clusters with node local flash. And since then, there's a number of different nodes. Sierra, I think, is top second. It has node local flash, and Summit, and so forth. So this is what we've been working with. Okay, so let me go into some of our use cases and the motivating applications that have caused us to shape the libraries in the ways we have. So what is metagenomics? Metagenomics means that you scrape the wall, let's say, of the subway in New York, and then you run the sample, that's your sample, through a PCR and amplify the genetic material that's there. And then you try to figure out, are there pathogens? What is in there? What is the content? So that's metagenomics, because there are a number of different organisms in there. And the reason that I really like this particular application and our use of it is that having a large capacity of memory changed the way that we approach the problem. So Jonathan Allen, who is the bioinformatician at the lab who I worked with, I went to him and said, suppose you had terabytes of memory local that you could just access, how would you approach metagenomic analysis? And he said, well, normally I would use sequence alignment. So you have a reference genome and you're trying to align the fragments that you've gotten to that reference genome. But if I had a very large memory, I'd have this huge hash table, and I would just look up the fragments, and from my database of my reference genome, I would be able to figure out what the likely source of this particular fragment was. So this really changed the way that they operated. The code is open source, and so in a day on a small cluster, they could search the complete collection of human microbiome, or in a couple of hours, search a single Illumina next-gen run on a single compute node. So this was a real innovation and a completely different way of doing things, enabled by large capacity memory. Well, what did we learn? Well, we started out trying to use STL and discovered that libraries and data structures optimized for DRAM didn't work when you have a backing flash. And so we had to change the way the data was laid out for locality in order to exploit that. So while the high capacity led us to a different way of doing the algorithm, we also needed to go further and adapt the data structures and the methods of accessing them to take advantage of page, in this case, page locality. We also discovered that we needed a large amount of concurrency to effectively utilize flash. And then, there's been just some discussion in the past couple of days of keeping binary data structures and just putting them out in persistent memory and reading them back. And this was our approach, but we discovered some gotchas there in if you don't have complete compatibility between compiler versions, machines, and even the program that's generating the large database and the program that's reading the large database, you can have some very subtle gotchas. So binary data is good, but there are some problems that you have to work around. The second application area, astronomy. So here we're talking about an optical telescope and we have extremely massive data sets reaching the petabytes that we want to scan portions of to look for asteroids. So it's called, the application is called transient detection, so transient objects we're trying to look for. And one more simplified way of doing this is to imagine that you have an image cube. So the image cube is the successive time series images taken by through that telescope. And so what we have done is using UMap, which is a user space mmap handler. We imagine that we have a virtual 3D cube. We find an object that might be a transient and try to trace a vector through the time series to discover whether that's actually the case. And so behind the scenes, the handler, based on the IJK of this virtual cube, is going to find out what files, so there might be hundreds to thousands of files, small files that make up this composite image. So what file is it in and what offset? And then build a page based on that particular reference. So the transient detection used, as I said, this UMap handler, which is an mmap page fault handler that uses the user fault FD feature that's been available in Linux since 4.3. So the idea is that the application maps in a virtual range. So it's not a file backed, it's mapping in a virtual range anonymously, and it registers the UMap handler for each of the ranges that it might have mapped in. And then the handler maintains the page buffers, fixed page buffers. It pulls a message queue from the kernel for page faults. And when the kernel writes these page fault events to the message queues, the handler threads then service that page fault. And then they do eviction on their own. So this is a separate buffer that's not the page buffer for the file system. The code URL is there. And this I won't go through in the interest of time, but I'm leaving it in the charts if people want to look at it later. The idea is that we have multiple kinds of worker objects. We have to be self-load balancing because certain parts of the virtual range might be hit more heavily and have more messages generated for page faults than other areas of the range. And so it's a fairly complex, highly concurrent handler library that is bound with the application. As far as lessons learned from this experience and ongoing lessons that we're learning, the prior version of this was called DIMMap. It was a kernel module, And given the heroic efforts to upstream things, the way it was written was more of a seat of the pants kind of approach, that we had some Red Hat people look at the code and just kind of shake their, no, this will never do. And then it was really hard to track kernel revs, and UMap got better and better. And so we saw this user fault FD as a more user level as opposed to a SIG fault handler. And so we thought, let's see if we can make this work. Yes, it's in user mode, it's not as efficient, but on the other hand, because it's a library, part of an application, we can do a lot of things to customize it for what that application needs without affecting the rest of the system. And so, for example, we can say, well, our page size is 4 megabytes or 3 megabytes, whereas the system page size can still be 4K, but that's the amount that we're going to read or write for this particular application. We can set a read-ahead amount. Again, it's just for this particular application. And we even have a gather list, which we use for the transient detection, that here are the pages, here are the indices of my array that I'm going to be needing in the future. So we've learned a lot in how to do this, and we have seen that we get better performance with proper tuning of parameters that we can do with our library. We also have learned the handler has to be highly multi-threaded, and the application has to have a high level of concurrency to make this all work. So now our graph expert.
So my main obsession for the last almost 10 years now has been graph analytics at scale. And really, we're trying to help data scientists process very large data sets in the billions, trillions of vertices and edges, and heterogeneous types of graphs, not just simple sort of textbook graphs. The analytics that we're interested in are things like search and ranking, pattern matching, and clustering. I won't talk about those in detail today. I'll talk a lot about breadth first search, which is sort of our main workhorse for evaluating different things. And the main reason why I'm interested in persistent memory is because constructing and indexing these graphs is often very, very time consuming. It can be many orders of magnitude larger than operating whatever algorithm you want to run. And then also, we often want to update a graph after it's already been built, append new information to it. And that persistence and consistency is important to achieve that. So we've been at this for a number of years. As Maya mentioned, we've been using Catalyst, which is now close to end of life. But I use this plot to show the power of using, in this case, PCIe NVRAM to store graph data for data sets. So this is the largest open source graph data set. It's a web graph with 128 billion edges to it. In its original directed form, takes about 1 terabyte of space. And then in an undirected, if you have to symmetrize it for certain algorithms, it's about 2 terabytes. And what this chart is showing is 4 textbook graph algorithms: breadth first search, PageRank, connected components, and K-core. And I use this chart to illustrate 2 things. One, the strong scaling of our distributed algorithm, which isn't the point of this. But what I think is interesting for this conference is the difference between the blue line and the red line. So the blue line is, in a strong scaling plots, the blue line is when there's insufficient DRAM to process this graph, and we're forced to spill to the node local storage. Each compute node of Catalyst has a 700 gigabyte SSD, and so it takes 2 compute nodes to store the directed version of this graph. And then in the bottom 2 plots, we're operating on the undirected graph, so it takes 4 compute nodes. And then as we strong scale, using more and more compute nodes up to 256, at some point we're able to now fit this graph, this data set, into main memory, and we can switch over to the red line. And that gap there between the blue and the red at either 16 compute nodes or 32 compute nodes is really the overhead of us going through memory map versus having it in traditional heap memory. We also use this particular graph to test out other open source graph frameworks. This is a very challenging graph, and not many frameworks can even operate on this data set. We also participated in the Graph 500 for a number of years, all with some form of persistent memory. Most of these are NAND flash, all of these are NAND flash. Some are SATA or SAS drive in the old days. We rode the Fusion IO train for a long time, And then now we have NVMe devices inside of Sierra. But if you're not familiar with Graph 500, it was designed to, the data-intensive community that wanted to create a benchmark to complement the top 500 ranking of supercomputers. And they chose breadth-first search on a large scale-free graph that had a scale-free graph refers to the power law distribution of vertex degrees. And the generator is capable of generating very, very large graphs if you so choose. And to date, our largest, and it's also the largest on the list, is on Sierra using the NVRAM that's inside of each compute node. We have 1.6 terabytes of NVRAM per compute node, 256 gigs of DRAM, and spilling out to that NVRAM, we've been able to process 70 trillion edges. And doing so, we're able to do it in just 15 minutes. And we feel that this is a pretty, while it's much slower than an in-memory optimized algorithm could do on a smaller data set, 15 minutes to traverse 70 trillion edges is quite practical for many applications. And so some of the lessons learned that we've had along this is having this large extra capacity has led us to many different graph algorithmic innovations. We've focused on semi-external graph algorithms where we're manually partitioning different portions of the data based on their locality profile, and also had to drive high concurrency algorithms for latency hiding to the flash, to the NVRAM. We had a rough start using memory mapping out of the box, going back to the Linux 2.4 days. And in response to that, we've developed a user space cache that we used for a little while. We started a project called UMap that we've since been followed by UMap that Maya just mentioned. And fortunately, as newer kernels, the 4. kernels and the 5. kernels, we're seeing much better improved performance for read-only workloads. The biggest win that I see from an applications point of view is the workflow. That the ability to attach to a previously created data set is very, very powerful. And it made us start a search for allocators, persistent allocators 5 years ago. And we used Boost in a process for a long time. And there was a number of talks I've seen just today talking about C++ allocators. Boost in a process did many of these things 5 years ago. It was a really great library. It had nothing to do with persistence. They didn't care about persistence. And that's forced us to develop something we call Metal, which is taking the Boost in a process interface for C++ and changing out the underlying allocators so that it's a more persistent memory-friendly allocation algorithm. But I really think that this workflow benefit is really overlooked. It's a very subjective thing, but this is really, I think, where the win will be, not in the raw performance. So we have 3 success stories now. So where's our problem? Well, all of 3 of these success stories we have been read-only applications. In fact, we've had to work hard to generate the data sets in a non-out-of-core way so that then we can operate on them out-of-core in a read-only way. And I believe system software has been our largest impediment to success. When we profile applications that are trying to do reads and writes, so mutating the persistent memory, the performance that we see through I/O profiling is much lower than we know the devices are capable of. And we think file systems and paging are really a lot of those bottlenecks, and I have a chart that I'll bring up in a few slides to illustrate that. So the persistent world as it should be, according to me. So I think that we need the ability for application developers to create custom, complex, persistent, and consistent data structures. So we've been advocating the memory mapped approach, and I mentioned we started off with Boost in our process and are transitioning to new allocators. But this persistent and consistent is really not a trivial thing, and we don't have the right answers to this yet. We're working on it. It's my personal belief that fine-grained consistency is really not practical. If you have to rely on fine-grained cache line flushes to persistent memory, at the same time persistent memory is 5x slower than DRAM, you have a problem. Oftentimes, it looks like we're taking out traditional lock-free algorithms and adding flushes to them, which we wouldn't have done in the lock-free, in a traditional lock-free environment. But more important for my work is that managing multiple disjoint persistent memory regions in tandem, think distributed persistent memory, can't take this approach, because if one compute node crashes and I have data sharded across all of my partitions, I have to roll back to some prior consistent state. So we need bulk consistency, we need snapshotting, we need versioning, where we have a backup to some sort of with some storage capacity. And this is what we've been working on, but again, we have not solved this problem. So a postdoc in our group, Keita Iwabuchi, has been working on a allocator, we call it METAL. It's a meta allocator for persistent memory. And unfortunately, I don't have time to really do justice to his work. I'll just quickly highlight it. It's a C++ allocator for STL-like containers. We've built heavily on top of Boost Interprocess. And it is more concurrent than Boost Interprocess, because we know that concurrency is very important. And we've been working on this persistent model, this snapshotting. How do we snapshot the region? And our goal is to develop this allocator for file-back persistent memory, whether it's Optane type with DAX or whether it's a NVMe SSD. And there's three main use cases that we're after. The simplest is just a persistent in-memory data store. Where I'm personally more interested is in the snapshotting checkpoint. So an application will have a database that is periodically at its choosing peeling off versions of its memory space. And then for more traditional simulation applications, we think that the producer-consumer model might have a benefit, where we have a producing application that's writing to persistent memory and maybe visualizers attaching to at consistent snapshots of that database. We have a C++ interface, very similar to the ones we've heard about today. And again, we're building off Boost Interprocess. This is an illustration of how one would use Metal. You basically create a manager, give it a path to some file system where you want to work on it. You can construct objects. You can name objects so that you can reattach to them. It uses offset pointer like Boost Interprocess does, so we don't have to worry about mapping it back to the exact same location. And then we explicitly call a sync function. So we have this explicit sync that's in there. That is not implemented currently in an efficient way. It's very naive. We've been playing with semantics here. So let's talk more about our more recent experiments. So using Metal, not in a distributed memory context, but using Metal with multi-threaded graph benchmarks that we've been playing with. We've done experiments on both Optane and new NVMe devices. We have two different systems, NVMe on the right and Optane on the left. These are very different systems. So I've aligned the y-axis here, which is in edges per second, so a rate of processing, but you really can't compare. We have an AMD EPYC processors on the right, and we have the Skylake on the left. And we're operating on a graph that scales. On the y-axis is the scale of the data. At the far right-hand side, the 30s are operating on half a terabyte of space. And so this box has 192 gigabytes of DRAM, so we're forcing it out of core. And this one has 256 gigabytes of DRAM, so it's also forced out of core. So our takeaway from this is that in app direct mode, we're about 2x slower than DRAM. And the NVMe is about 3.6x slower than DRAM. So still quite reasonable overheads for being able to scale to much larger data sets. And this is for a graph construction. So this is building the input, and it is done in a mutable way. Yes?
What kind of SSD is that?
I believe it's an HGST SSD.
It's not an Optane SSD.
No, it is not. We've played with them in the past, but this is not.
Those are probably significantly faster.
Our experience was that the level of concurrency necessary was lower, but the overall bandwidth, so this is really bandwidth bound, so throughput was not substantially higher. So in this chart, which is doing just breadth first search, which is read-only, we can measure how much bandwidth is happening just through IOStat, and we're hitting close to peak bandwidth of these devices. So this is breadth first search running on the previously generated graphs from the previous slide. Again, we're showing edges per second as on the y-axis. And here the differences from our out-of-core rate versus our final in-core DRAM rate is even smaller than in the mutable case. So here AppDirect is about 2.4 times slower than NVMe, or sorry, than its respective DRAM, and NVMe is 2.2 times slower than its respective DRAM. So I promised that I would have a slide that talks about our system software woes. And so I call this applying Persuasion to Linux to get it to do what we really want it to do. And these are the kind of tricks that we have to play to get to operate in this space. So in both of these charts, we're doing graph construction, so we're mutating the data. And what we discovered is when we would have a single large file, so a 512 gigabyte file that we would memory map into our application and operate on, we were getting really poor performance. And one day we tried, what if we chop it into 8,000 files and contiguously IMAP them so that the application sees a big virtual view, but under the covers, 8,000 files sitting in our XFS file system. And we see a 3x improvement. It wasn't what we expected, but we'll take it. The second thing that we often do is we tweak the VM tunables inside of Linux to force it to maintain a much larger percentage of dirty pages in its page cache. And this is because we're operating on an out-of-core data structure, and we only want to flush those pages if it absolutely must do that. Yes?
Do you know why that first, that's really bizarre, first NVMe was why?
So we think it's got to be file system related lock contention. We were just chatting at the break about that. The thing that we tried to verify if it was file system related versus VM related is we also took one large file and memory mapped offsets of it 8,000 times, and it was about the same speed as the one file. Now, I don't know if under the covers Linux is appending those virtual memory area, the VMAs, or not, but that was a test we ran. Okay, that's. Any other questions about graph before we move on to? We have 3 minutes, I think.
And so our postdoc, Intel very graciously lent us an Optane to try out. So for the past few months, we've, as I said, not the kind of in-depth that you've seen previously, but I think we can confirm what has been said before, that NUMA latency can cause the remote access to DRAM to be slower than local access to NVM. So this is something that we observed in some of our experiments that we did. And severe congestion on that intersocket link we've seen causes performance loss when multiple threads are accessing the remote persistent memory. So you really have to be careful about placement and NUMA sorts of things in using persistent memory. And then we're just about out of time, but I wanted to at least show some of the power and energy measurements that we've done, because that hasn't been mentioned yet with respect to Optane. And so this chart is showing dynamic memory power of various workloads: DRAM, DRAM cached, persistent memory is a NUMA node, and then DAX-aware file system. And so you can see the watts there is getting close to 60 watts for DRAM only. And with memory mode, of course, you're DRAM only, so it's going to show the same power. And then when you force it to be AppDirect and you're reading from the media, then the dynamic power goes way down. The chart on the right is showing that if you could tune your accesses, arrange your data structures and tune things so that perhaps write-heavy are in DRAM and read-heavy are in NVM, that you have a lot of choices here of playing with how much power you're using. So the x-axis is the percentage of reads, and the y-axis is the compute intensity. So it's kind of a heat map of the trade-offs there. And then the second insight that we had is that if we can isolate data structures that are write-heavy to DRAM while we're in transit and using them, that we can really, really reduce the overall energy. Things run a lot faster when you're not doing writes to the media, and you can save an awful lot of energy. And if you don't, the white line is showing what you're using if you are doing all those writes to the Optane itself. So just a couple of little more information about the power and energy profiles.
So just to kind of wrap up, almost more editorialize about what I think the state of data science is with Flash, is I really think that Flash and persistent memory can enable data science in very disruptive ways. It hasn't yet, but I think it can. System software continues to improve, but we really need improved system software, and we have to solve this consistency problem for our persistent memory regions. It is an ongoing research challenge. It's kind of a subjective claim for me here, but I really think that large persistent memory will allow data scientists to interact in real time at unprecedented scales. So I work with data scientists sort of in my day job, and they have to interact with the data. And for now, if they can't do it inside of Jupyter Lab or R, they're not going to work on it. And that lets them hit laptop scale data. But the ability to have large database in-memory data structures that we can attach to in real time without having to go through traditional serialization is going to allow us to, or allow the data scientists to interact at this human scales with large data sets. I think really that's where the power is going to be in the future. So, thank you. I think that yes and no. I think that it's an exploratory process where they want to apply transformations to the data, but they might want to undo those transformations. And that in a notebook, a Python notebook gives them that. They can go up a cell and go back to the state it was and try another. Basically, you know, in their search for whatever it is they're looking for, they have that interactivity. And things with persistent memory and versioning of the data so that we can basically let them have that environment, but on much larger data sets. I think that's the connection.